Hey, good morning, everyone. Today we're looking at section 3.1 homework, and it's got one problem out of section 3.2, and that's number 47. For some reason, this is 42. That is number 47. Cool. Okay, so this first 1 and 5, we're looking at the same function, and we're going to use the two different definitions of the derivative to find out the slope of the tangent line equation, or specifically in this case, the slope of the tangent line at one specific point at x equals 2, using the two different methods. So again, this 3.1 section is really expanding on just our polynomials we work on. We're doing more rational functions here. We're doing more radical functions, a cubic over here on 19. So let's kind of see how this works here. So again, I'm going to plug in. I want the slope of the tangent line for this function at 2. So that's what that whole use the definition of the derivative is. And if you notice, it's the 2 and 2 plus h model for number 1. And for 5, it's checking it at a specific point, x and a. So let's do this first one here. So I'm going to plug 2 into this equation, and I get 1/2. I plug in 2 plus h into this equation, and I get 1 over 2 plus h. And then I'm still doing y2 minus y1 over x2 minus x1. And I'm going to take the limit as h approaches 0. So I need a common denominator here. So I need to multiply this by 2 plus h over 2 plus h, like that. And again, what I like to do is I like to do plus and -1 to make sure I distribute that negative across the entire thing. And then I'm going to multiply this by 2 over 2. So when I do that, I get 2 times 1 is 2. That's that 2 there. And then I got to distribute this -1 across both of these. So I'm going to get -2 minus h. Don't forget that it's the most common thing people do, is they'll forget to distribute that minus across both those terms. So I'm going to leave this denominator nice and multiplied together because I'm going to look to factor things out or cancel things. Okay, so then I get 2 minus 2 minus h over 2 times 2 plus h. And all of that is over that h in the denominator there. So these cancel out here. And I'm just left with minus h over 2 times 2 plus h. And writing in old school, divided by h is the same as times 1 over h. So now I'm seeing these things linked together here. I got rid of the complex fractions, and I can cancel out that h with that h, and that's leaving me with -1 on top. Don't forget that's a -1 up there, and then 2 times 2 plus h on the denominator. I'm taking the limit as h approaches 0. So it's -1 over 4 when I plug in. So that is the slope of the tangent line of the 1 over x function at 2. So we can kind of check that real quick. Make sure that works using our little calculator trick here. Give this 1 second. Do this. So let's plug in our function 1 over x. Let's graph it. There's 1 over x, and I'm checking at 2. So second, calculate dy dx, which is number 6, at 2, and I get negative 0.25. So it's -1/4 with a little rounding error is my answer there. Okay, so that's something we've been doing since the last unit. This is the new definition of the derivative. So two different ways to look at it. So in this case, I'm going to plug in 2 into the equation, get 1/2 again, and plug in x to get 1 over x. And I'm still going to do y2 minus y1 over x2 minus x1. Only now I'm going to do the limit as x approaches 2. I need these two values to approach each other. So it's still plugging in 2, plugging in x, plugging in two different values, and then still making those values really close to one another. So instead of h approaching 0, like the width between the 2 points getting smaller and smaller, now I want these 2 points to approach each other. So again, if I plug in here, if you notice, I'm still getting 0 over 0, indeterminate form, more work to do. So I need to do, a little work to get these denominators all together here. So I'm going to multiply this by 2 over 2, multiply this by x over x. And if you do that, you notice I get 2 minus x on top, and then this common denominator of 2x on the bottom here, all over x minus 2. So there's a little trick here. If you notice, this and this aren't going to cancel out. They're close, but they're not exactly the same. So I'm going to do two tricks here. I'm going to factor out a -1 out of this here. If I do that, I get negative times -2 plus x, or x minus 2. And then, so that is the same as that denominator with a little negative factored out. So this is -1 times x minus 2 all over 2x, and then divided by x minus 2 all of this divided by x minus 2 is the same as times 1 over x minus 2. And then if you notice now, because I factored out that negative 1, those two things are exactly the same. So I'm left with negative 1 over 2x, and now I'm going to plug in that 2 for x. And if I plug in that 2 for x, I'm still getting the negative 1/4. That same answer using the two different methods for 1 and 5. So that's the trick there in the rational functions, is to simplify the complex fraction. There's a little trick here. So same method, this alternate definition of the derivative method here. I'm going to plug in 3 into this. If I plug 3 in, I get square root of 4, which is 2. I'm going to plug x in, and I get square root of x plus 1. So I have my 2 points, and I'm still going to do y2 minus y1 over x2 minus x1 to get this. Only now I still want the limit as x approaches 3 using this new definition of the derivative. So if you plug in here, you notice you're still getting 0 over 0, indeterminate form, more work to do. So the trick with these are to rationalize the numerator. So again, just something FYI, that's how we're going to do these. So if I rationalize the numerator, if I FOIL this numerator here, I get x plus 1, because radical x plus 1 times radical x plus 1 is just x plus 1. And then the outer terms is plus 2 root x plus 1, and then the inner is minus 2 root x plus 1. So those cancel out, and then this times this is minus 4. Okay, so I'm getting rid of all of that. And for my denominators, don't FOIL these out. Just stick this times this and leave all of that stuck to each other in the denominator. Because what's going to happen here is, if you notice, I get x minus 3 in the numerator, and that's going to directly cancel out with that x minus 3 that was in the denominator, since everything was still all factored. If you FOILed it, we wouldn't see that. So I'm going to leave that denominator multiplied together, but the numerator I need to clean up. So when I clean that up, I have 1 over root x plus 1 plus 2. And then I can plug in the 3. If I plug in the 3, I get root 3 plus 1, which is root 4, which is a 2 plus the other 2 over 1. And so for this function, at this point, I'm getting 1/4 as the slope of the tangent line. Just to check that, let's do square root of x plus 1. I'm checking that. So every point should have a positive slope. I'm kind of saying that, so let's check second. And I'm doing dy dx, 6 at x equals 3, and I'm getting that 0.25. So 1/4 or 0.25. So for this function at x equals 3, that's the slope. Okay, cool. So now 13, 14, 15, and 16. I'm going to go check out the book here. So I'm given some functions here. And I want to match up. So these are derivative graphs. So these are slope graphs. So I'm starting with this 13, 14, 15, and 16 here. I don't know if I did make a sketch of what this derivative graph would look like. Again, the derivative being a function itself. Well, let's see. Over here, all these slopes of the tangent lines are negative, so the graph should be negative. And if you look here, it turns, so that slope is 0. So the function should have a 0 value there, and then positive value. So if you're trying to make a sketch of what the derivative graph would look like, it should have negative values, and then a 0 value, and then positive values. So where do I see that? Well, right here. I'm seeing negative values, and then a 0 value, and then positive values. Again, the y values on this graph tells me the slope of the tangent line on this graph here. For 14, if you notice, these are all positive. These stay positive the whole time. There's one spot where it kind of turns and it looks horizontal, but then it stays positive. So for this graph here, I want all positive y values because the slopes are positive here, here. And then at one point, I need the slope to equal 0. And then to stay positive again. Well, that's this graph here, because these have positive y values, a 0 y value, and then positive y values. So again, this one was B, and this one was A. Okay, so for this 15, oh gosh, we got a lot of action here. So it's like positive, positive, then 0, and then negative, and negative, and then 0, and then positive, then 0, and then negative, and negative, then 0, then positive, and positive. So just kind of starting here, I need a 0 value at x equals 0. So that's this one here. It could also be this one here, but I feel like it switches a lot more. And then it's negative values until this point here, and then 0 again, so right around there. So these are all negative values there. And then it's going to start to just go positive values for this whole thing. So then it's all positive here. And it's just repeating. So, going from left to right, all these different values here. If I go to the left, it's all positive here up until about this point here. It's going to equal 0. So it's at 0 right about there. And then just positive values that whole time. Again, this is tough here. So this is our first kind of opportunities to check out like derivative graph sketches. So kind of a tough thing, something we're going to keep coming back to. And then here, if you look, this is all negative slopes here. So this graph needs to have all negative values. So I'm seeing all of that sort of matching up with these two graphs here. So it looks like this is setting up for D. Okay, that was the tough one. And now let's look here. So this graph, it's all negative, and then it's going to teeter off there. So it's all negative values, and then it's going to turn. So negative values, and then it's going to turn. And then I got positive values for just a little bit, and then I'm turning again in 0. So this should have a y value of 0 because the tangent line is going to be horizontal at 0 here. At this point right here, being horizontal means a y value of 0 there. So then they're all positive before that. And then it's this graph is decreasing for a little bit again, meaning the slopes are negative, meaning this graph's going to be negative for just a little bit more. And then from here, where it turns again, this graph is going to have an x-intercept there. And then for the rest of the time, all of this is going to have positive slopes. So that means this graph is positive. So those are tough. So that is graph C, our first chance to kind of play around with graph sketches. And really what the focus on is when these graphs turn, these graphs are going to have x-intercepts. That's the main focus. And when this graph is decreasing, this graph is going to be negative, and when this graph is increasing, this graph is going to be positive. So again, when the original graph is decreasing, derivative is negative. When original graph is increasing, derivative is positive. And when original graph is turning, this graph has an x-intercept. So hopefully you're fun with that. That's something we're going to keep coming back to, this idea of the graph sketches. Okay, so that's all there. Okay, so here's what's interesting, a new way to kind of look at this here. So what 17 is asking or saying is, what's the tangent line and normal line? And it gives us just this notation here. We need to translate what this means. This is talking about a function value. That means what this means is if you put a 2 into the function, the output is 3. So that's a point. That means this graph has the point 2, 3. And then it says f prime of 2 is equal to 5. Well, this is that new notation. This is talking about slope. This is talking about tangent line. This is talking about derivative value. At x equals 2 equals 5. So what this is saying is the slope of the tangent line at x equals 2 is equal to 5. So that's a slope value there. So with my point and my slope, I can create my tangent line. Y minus 3 equals 5 times x minus 2. And then with my tangent line, I can create my normal line, just taking the opposite reciprocal slope of that. So there's my tangent line and there's my normal line, but analyzing what this notation means. This is talking function values, so this is talking points. And this is derivative value, so this is talking slopes. So at x equals 2, the slope of the tangent line is 5. Okay, so here's our cubic. So again, just doing a little more harder algebra. I'm going to use our first definition of the derivative. So I'm going to plug in 1 into this. And 1 plus h, a point really close. So if I put 1 plus h in, that's 1 plus h cubed. So you can use your binomial theorem or however you want to multiply this out. I just multiply 2 of these together first to get 1 plus h, which is 2h plus h squared. And I'm going to multiply this by 1 more to get all 3 of those multiplied together. And if you do, you get 1 plus 3h squared plus h cubed. So this is my y2. So all of this, y2 minus y1 over x2 minus x1. And I'm going to take the limit as h approaches 0. And that is my derivative value. That is my f prime, using my new notation, f prime of 1. I'm going to take, get those 2 points really close to one another. 1 and 1 plus h getting really, really close to one another. So again, I can cancel out these ones because those cancel out. And then if you notice, you can factor and cancel an h out of every term. So if I take an h out of every term, I'm left with 3 plus 3h plus h squared, and then cancel the h out with the denominator, then plug 0 in here, and so those two terms are gone, and I'm getting 3 is the slope of the tangent line for this function at x equals 1. If we want to verify that, second, calculate 6 at x equals 1. It's equal to 3 with a little rounding error there. I'm seeing that slight rounding error there. Okay. And then, okay, so let's finish this one up here, sorry. So then I have my point, 1, 1. I have my slope of the tangent line at 1, 1, which was equal to 3. So with my point and my slope, I can dump everything into point slope y minus 1 equals 3 times x minus 1. And then the normal line, again, same point and just opposite reciprocal slope. So tangent line, normal line. Okay, so for 22, you're given a graph that looks something like this. And it says, make a sketch of what the derivative is going to look like. So if this is the original function, this is my y value, make a sketch of what the derivative graph looks like. And just to kind of really hyper-focus on this point and this point. At -2, it looks like this graph is turning. So the slope of the tangent line, if you did draw a tangent line in there, something like that, the slope's going to equal 0. So that's going to be an x-intercept on the derivative graph. And at 1, I'm seeing the same thing. So at this min here, I'm seeing that the slope of the tangent line is going to equal 0. So that is going to be an x-intercept on the derivative graph. So I'm seeing this graph increasing. This graph is positive. This graph is decreasing in between -2 and 2. So this graph is negative. And then this graph is increasing to the right of 1. So this graph is positive. So again, when a original graph turns or has this min or max point, that's going to be an x-intercept on the derivative because the slope of the tangent line is going to equal 0. When this graph, the original graph, is increasing, the derivative graph is going to be positive because the slopes of the tangent lines are going to be positive. And then when the original graph is decreasing, the derivative graph is going to be negative. And when this graph is increasing, the original graph, then the derivative graph is going to be positive. So just kind of playing around with this idea in 22. And 24 is kind of doing the same thing. So it just gives us some graphs. But if I was going to do a little sketch here, let's see here. So I have this little hook here, which is the graph of x ln of x minus x. For some reason, it looks like this. Okay, so be it. But what I'm going to focus on is really I'm going to focus on this min here. So it looks like I have a min that's at exactly 1. Kind of drew it up, but it's like right there. Okay, so that min on this graph has to be an x-intercept on the derivative graph, on the y prime graph. And if you notice, this graph is negative. Sorry, this graph is decreasing. The original graph is decreasing. So then this graph is going to be negative. And then this graph is increasing. So this graph is positive. So if I just kind of do a kind of general sketch like that, so like -0, positive, it's starting to shape up like the natural log of x graph. And if you look at kind of all those graphs, it's definitely not sine, it's definitely not x squared. It's not the line 3x minus 1, because 3x minus 1 has an x-intercept over here. And it's not square root of x, because square root of x is always positive. So the only graph that's matching up is this natural log. And again, we're going to get more into the idea of like, why is this more of like a vertical asymptote here? Like, well, is this getting really steep right here? Like really steep, something like that. Cool. Okay, so that's 24. Okay, so 26, this is a classic calculus problem. We started with an f of f graph that's a bunch of line segments, and it wants us to sketch the derivative. So what's interesting about line segments is you know what the derivative is going to be. It's going to be that value that is the slope of those line segments. So from this first section that has a point at -4, 0 and goes to 0, 2, so that graph goes up 2 over 4, which means it has a slope of 1/2, that first section. So I'm just going to draw anywhere between -4 and 0. The derivative is going to have a value of 1/2, because that's the slope of the line. And then just to the right of that, between 0 and 1, I have a line that goes from 0, 2 to 1, negative 2. So if you go from 0, 2 to 1, negative 2 on the original graph, that goes down 4, because it goes from 2 to negative 2, down 4 over 1. So it's got a negative 4 slope. So anywhere between 0 and 1, the derivative is going to have a value of negative 4. And then if you look from 1, negative 2 to 4, negative 2, that's just a horizontal line. So that slope is 0. So I'm going to have y values of 0 that are on this graph, on this derivative graph. This is a f prime graph here. And then from 4 to 6, let's see. So from 4 to 6, that line segment goes from 4, negative 2 to 6, negative 2. So it goes up 4 over 2. So up 4 over 2 is a slope of 2. So again, like since all of the original graph has line segments, you're going to have constant slopes in each of those segments. So the derivative graph is just going to be these lines, these horizontal lines with those different y value slopes of the original line. And if you notice, I have the endpoints because for reasons we'll get into a little more later, but I have the slopes here. But at like 0, 1, and 4, the original function is not going to be differentiable because those are corners. So that's why I have open circle and open circle at 0, because the slope changes from 1/2 to negative 4. So since the slope from the left does not equal the slope from the right, the original function is not differentiable at 0, which means this graph is not going to be continuous. I'm going to have little holes there. If you're not differentiable, you can't put a point, because if you put a point on this derivative graph, that means the slope of the tangent line at that point equals that value. So kind of interesting there. So like, where is the original function not differentiable? Well, it's going to be at 0, 1, and 4 at those specific x values. Okay, so 27 is saying like, okay, kind of like the flip of that. If you know the derivative is equal to 1, and then the derivative is equal to negative 2, that means over here, it's going to be y prime. Sorry, I messed that up there. That means to the right of negative 1, you're going to have, this is going to be like the line y equals negative 2x plus something. Plus, I'm going to put, actually, I don't know if it's 1. I don't know what it is. I'm going to put some number here. And then to the left of negative 1, it's going to be like y equals x plus something. So I need this stuff to connect up here. And I know that the original function also has f of 0 equals negative 1. So what I need to do is kind of a tricky one. I need to draw a line that goes through 0, negative 1, but also has a slope of negative 2. So we can play that old game of 0, negative 1 with a slope of negative 2. I can plug that into y equals mx plus b to solve for that point. But it's really it's going to give me that value here, because it's going to be negative 1 here, because that is the y-intercept. So again, negative 1 is equal to 0 plus b. That is the y-intercept, because that is the 0, negative 1 point. So then I can just draw in negative 2x minus 1. I'm just going to draw that piece here like this. And it's going to keep going on in that way. And then I can draw the line y equals x, like a slope of one line, but I need it to connect up here. So not like the line here, y equals x, because then it wouldn't be continuous. I need this function to connect up over here. So it's going to be like that. So it's going to be, if I keep going over it, it's going to be like x plus 2, because it's going to keep going up to here. So the idea here is, if we have a constant slope of negative 2 that's what the f prime of x is telling us, that means the original graph must be a line. So it has to be a line of slope 1 and then a line of slope negative 2, and just getting those pieces to connect up to make it continuous. So kind of working backwards, kind of tough to do. So hopefully we're having fun with that. Okay, so 31. So this is saying it wants us to use one-sided derivatives to show that this thing does not have a derivative at 1. Well, that's kind of a trick question, because the first thing I always check for if something is differentiable is I need to check if it's continuous. So if I check here, if I plug 1 into this, the limit from the left, I get 2. and then the limit from the right, I plug in 1 into this, and I get 1. So since the limit from the left does not equal the limit from the right, the limit does not exist. So this function is not continuous at x equals 1, so it cannot be differentiable. So that's kind of like a trick to say, like, we're not going to fall for your little trick there. So hopefully you had fun with that. Okay, so now 3.2, number 47, it wants us to use the calculator to sketch the derivative and things like that. So I'll kind of go through the notation, what it's saying, kind of a good recap on how to graph a piecewise function. So let's see here. So we're going to put in x squared first, x squared, close that up, and then x, then second test, number 6, the center equal to 0. So x squared, x is equal to plus the function 2x, x second test, and that's greater than 0. Okay, so you got to put each function in a parenthesis, and then you got to do kind of the logic test there. And how you get to that symbol right there is you hit second math, which is test. And then so you close parentheses on that, close parentheses on that, and then add the second function. If you do that, you get this piecewise of x squared and then 2x. So I'm definitely seeing a corner happening here. So some issues with differentiability, but this is continuous because if you check, x squared and 2x both equal 0 at x equals 0. So this is a continuous function, but it's looking like it's not differentiable at 0. Okay, so part A just wanted us to graph this and remind us how to graph this thing here. I'm going to change the little window. It wants us to zoom in on this window here. So it says from negative 4.7 for some reason to 4.7. And then it wants us to do negative 3 to 5. Just kind of playing around the window. Okay, so here's this little guy here. And then, so it just wanted, so part B is saying, hey, look, the y values and f of x are the same. Sure, we can graph it by hand and check this, and that's all good there. Okay, now it wants us to do the derivative, the numerical derivative. So I'm going to do that on y2. I'm going to turn this off. And then on y2, I'm going to hit math, and then either go down to number 8 or just hit 8. And then again, we have to do ddx, put the x there, and then we do alpha trace for y1 for all x values, x equals x. Okay, and if I just graph that, it's going to take a second here, boom, and boom. So if you notice, this function is not continuous at x equals 0. And what that's telling us is that the original function is not differentiable at x equals 0. So I'm seeing this slope have a dramatic change. That parabola was coming down with negative slopes, and then it's turning. So it's negative, 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 and then 0. But then immediately to the right, the line 2x has a slope of 2. So it's immediately changing to a slope of 2. So we're seeing kind of that happening here. So it wants us to check what's the function values at negative 0.1 and 0.1. I'm just going to use my table for that. You can use your trace function, but I'm just going to do this and then do 0.1s. And then if you notice, again, at the corner, remember corners are bad. The calculators are really bad about finding function or derivative values at corners. It's not going to catch it because it uses that symmetric difference quotient. So we have to kind of do some investigation here. So if I wanted to check to the left, at negative 0.1, I'm getting negative 0.2. And to the right, obviously, it's always 2. So I'm seeing that always to the right. So we're seeing that derivative from the left and the right not equaling the same thing for that end derivative. So this function is not differentiable at x equals 0. So hopefully you had fun with that homework. I think that was it. There's our graph there, and there's our derivative graph. So remember, there's going to be open holes there because this function, the derivative graph is going to have a discontinuity because the original function is not differentiable. If I put a point on this graph at 0, that means that you can draw a tangent line, because every point on the derivative graph says, oh, look, the y value of this graph is the slope of the tangent line for the original function. So hopefully you guys had fun. I'll see you guys next time.